Hello everybody, my name is Shannon Clayton and I would like to present my tsunami warning system. In 2004, one of the deadliest tsunamis in recent history decimated populations in the Indian Ocean. Now among them were people who lived on this island called Sri Lanka. They had no warning, which led to the deaths of over 200,000 people. My design question for this internship is how can I design an effective tsunami warning system for the people of Sri Lanka? There are 3 criteria that I needed to keep in mind as I was designing this warning system. First, I needed to consider my warning time. Now, warning time is important because if I can give enough warning time, it'll give people more time to get to higher ground and to get to safety. Second, minimal false alarms are important because a high number of false alarms may cause people to ignore the warnings, and ultimately that would put them in danger. And lastly, I need to consider the cost for the warning system. The cost comes from the same account as schools, bridges, and roads, so I had to try and keep the cost low. In order to help you understand the science behind tsunamis, you need to understand how they relate to convergent plate boundaries, underwater earthquakes, and energy. During plate motion at convergent plate boundaries, one plate's going to slide underneath the other. This is called subduction. Now, earthquakes at or near convergent plate boundaries, earthquakes occur at or near convergent plate boundaries, but not all earthquakes cause a tsunami. Now, students, I'm going to pause here so that you know that you will need to include this type of information on your own slides, and you fill in the blanks for the information that I left, including how energy is related to tsunamis. During my research, I learned that there are 3 different types of sensors which I could use in my design. So there are earthquake sensors, shallow sensors, and deep sensors. And I had to consider both the pros and the cons of each sensor in order to use them into my design. Now, students, this is where you will explain some of the pros and some of the cons on all 3 sensors and how maybe knowing a pro or a con was helpful when you're trying to pair them together. For my first test, I just really wanted to see what type of data I would receive if I placed one of each type of sensor in an area where I knew that there were convergent plate boundaries and ocean-wide earthquakes. So I placed one of each type of sensor at these locations. The data I collected indicated that although I had 0 false alarms, not all of my warnings were being received, which was not a good thing. So I had several more tests in which I tried different combinations of sensors, and I finally submitted my 5th version to Hannah for feedback. You can see on the map that I included 1 earthquake sensor, which I placed on land. I had 1 shallow sensor, and I had, by that time, added 5 deep sensors. Now, the feedback from Hannah, she suggested that I increase my warning times by adding earthquake and or shallow sensors, that she said I needed more of those. And then she also suggested that I omit any unnecessary deep sensors. So I had to examine the earthquakes, really study those a little bit more closely to find out which ones I was missing or which ones were unnecessary. During my design phase, I realized how difficult it was to place equal importance on all 3 criteria. I decided I needed to have a trade-off. In my opinion, it was most important to prioritize warning time and cost because, first of all, I needed to make sure everyone had enough time to get to higher ground. And secondly, I wanted to make sure the cost was low enough so that it wouldn't affect the money set aside for schools, bridges, or roads. I mean, after all, if people need to evacuate, they need good roads to travel on. So that meant that the least important criteria for me was the number of false alarms. So I would try to keep that number low, but I felt like I could justify a handful of false alarms over a 50-year period. After a few more tests, I had my 8th version, which ended up being my best or optimal design. This is the design that I would like to propose to you for consideration. It's my best version because it had the highest warning time and it had the lowest cost. You can see that I used 1 earthquake sensor, 1 shallow, and 3 deep sensors. The data for my best or optimal design was very good. After I received Hannah's feedback, I made a goal of making it 50 to 60 minutes for my warning time, but my actual warning time was actually 67.25 minutes. Now, I did have a test where my warning time was 75 minutes, but the cost was way too high. And since those 2 criteria were most important to me, I didn't use that design. After I received Hannah's feedback, I made a goal of 0 to 1 false alarms. I actually had 3 false alarms. I did have 1 test where I had only 1 false alarm, but again, the cost was way too high, and I was really committed to keeping my costs down, so I didn't use that design. Lastly, I made a goal of trying to keep the total 50-year cost to about $84 million. This optimal design came in under my goal at just over $83 million. I didn't have any other designs that were cheaper, which is another reason why this was my best design. Let me take one last opportunity to summarize my plan and explain why my design is the best tsunami warning system for Sri Lanka. First, it offers a maximum warning time of 67.25 minutes, plenty of time for people to move to higher ground. Secondly, the total 50-year cost is only $83,306,000. In my opinion, this would not take away a lot of money from schools, roads, or bridges. Now, I realize there's an average of 3 false alarms, which Hannah seemed to think was a little high, but I don't think that that's a significant number. Only 3 alarms during 50 years? I think I can really justify that. Thank you for considering my proposal, and I hope you agree that it makes sense to adopt it for Sri Lanka. Thank you.